Hello everyone, let's solve some LeetCode today. So today we have this binary search problem, and this is a very trivial problem. This is kind of simple, but it is actually used as a sub problem in different hard problems. So a lot of the times what happens is that people just insert binary search as a concept in a problem, and they expect us to just think that okay, binary search should be applicable here. Although binary search itself will not solve the problem, but it is somewhat of a necessary step in those hard problems. Plus, this kind of problem, the binary search is usually asked a lot in interviews, so it's better to have it in your arsenal. So here we have this question, given an array of integer nums, which is sorted. So the array needs to be sorted for binary search to work. Binary search cannot work in an unsorted array. Now the sorting is in ascending order here, and we have an integer target. Now we have to write a function to search for the target in this nums array. Now, if the target exists, okay, return its index. So we are not supposed to return the number target. We are supposed to return the index at which this number is present in the array. Then, otherwise, if it's not present, then simply return -1. Simple, right? Now, of course, they are saying you must write an algorithm with order of log and complexity. Okay, so we are not supposed to just to go through the entire array and write an algorithm that is running in linear time complexity or order of n complexity. We are supposed to write an algorithm that actually takes order of log n. So basically, which algorithm takes order of log n time complexity? Simple, binary search. It's pretty self-explanatory. It's just, let's first of all try to understand how these things are gonna work. -1 0 3 5 9 12. Okay, we have this array. Now we are supposed to find a target, and in our case the target is 9. Figure out where 9 is. So one brute force way is to, of course, run a loop, okay, and go from 0 index to all the way to this n minus 1 index. Okay, 0 1 2 3 4 5, that is fifth index. You go from 0 to fifth index and you will find where the 9 is. But then again, this brute force algorithm will take order of n, because you are going to go through every single element just to figure out where the 9 is. And we are not supposed to go through every element just to find our target element, because we want something that works in log n, okay, where n is the number of elements. So here we have these elements and we are supposed to find 9 here. So what we can do is, well, first of all, we can create pointers, okay. So we have a left pointer and then we have a right pointer at the extreme ends, right? So left pointer is pointing to 0 index, right pointer is pointing to fifth index, that is the end of the array. And now we can actually, try to think something. So what we want to do is we want to eliminate the possibilities. We want to basically eliminate where the 9 cannot exist, in which part of the array the 9 cannot exist. So what we can do is we can try to select directly L. So L is 0, and if we select L, then we have the number 1 -1. And is -1 equals to 9? No. So what we will do is we will simply mark it invalid, right? But listen, okay, if even if you mark it invalid, you still have to actually kind of go through the entire array, like, again, okay, you have to go through the entire elements of the array. So let's try to actually do this for right. Okay, let's just say right is what we choose. So right is 5 and its value is 12. Okay, so we compare 12 with 9. So is 12 is equals to 9? Of course not. So we cross it. It's invalid. We have removed one possibility, right, from the array, but it is still giving us the same issue. We still have to basically go through the entire array again. So by this time we can see that we cannot just go ahead and take single element and try to remove their possibilities. We need to remove a lot of elements at the same time in a single go, or we have to remove a lot of possibilities in a single go, so that we can create an optimized solution. And how we can do that? Well, we can do that with the help of middle. Okay, so if we notice, here we have two elements as the middle. Okay, and so if we compare 9 with 3, let's take it as our middle. If we compare 9 with 3, we see that 3 is not equals to 9, but 3 is less than 9. Okay, so 3 is less than 9. What it means is that anything less than 3 or 3 simply cannot be 9, because the array is sorted. Okay, this array is sorted. So sorted array means if 3 is less than 9, then anything before 3 should also be less than 9. So what we will do is we will now remove these possibilities. Okay, so all this stuff we will ignore it. And how are we gonna ignore it in terms of code? What we will do is we will simply take L and point it towards 5. Okay, so now L is this. Now our consideration of array is this. Okay, so this is the only concern we have. Now we will again try to find the mid element in the remaining this one array, and the mid element will be 9 this time. Okay, and so is 9 equals to 9? Yes, it is equals to 9. So we will simply give the index of this place. Okay, so we will simply give index of mid. So how do we find the middle element? Simple. So middle will be right and left. Okay, right plus left divided by 2. Simple as that. Okay, this will be our middle. Now if we found something other than 9, okay, something greater than 9, what we will do is we know that if this thing is greater than 9, then everything else till here will be invalid. Okay, so what we will do is we will simply shift the right to mid minus 1. Okay, so that's the kind of logic we actually perform in binary search. So here is a simple code for binary search. I'm using C sharp, but the Java is gonna be pretty much the same. So what we are doing here is we have this nums array, then we create two pointers, left and right. So left is 0 and right is at the end of the array. So nums dot length minus 1. Now we are gonna do this. Okay, we are going to run this while loop until and unless left is less than equal to right. Okay, and why is it? Because suppose that at any instance, let me just write it again, minus 1 0 2 and then 5 9 12 3 5 9 12. Okay, 3 5 9 12. Okay, we have a right here and we have a left here. So if at any point, okay, right becomes less than left, okay, it means that these two pointers actually interchange their position. It means that we have already gone through every single element in the array and we did not find the element that we were looking for. Okay, because now that the right and left have already changed or interchanged their places, we are simply gonna get the same elements again and again and again. No point in trying to do that. So that is why we are running our loop only for left less than equal to right. So while left is less than equal to right, what we are doing is we are trying to figure out the mid for those particular left and rights. So we add the left right divided by 2, we have the mid. Okay, then we check does the nums of mid double is equals to our target. So do we actually have the target? If not, we go ahead. If we do find the target, we simply return the mid index because we are supposed to return the index. So here we will find the target and we will return the index. But if we did not find the target, what we will do is we will check if the nums of mid is less than target or greater than target. If it is less than target, then we know that the index middle and anything before it is simply not going to be the answer. So we will shift the left pointer to mid plus 1. Okay, the thing that we did here, we shift the left from 0 to mid plus 1, that is 5. Okay, similarly if it is greater than the target, what we will do is we will shift the right pointer from end to mid minus 1. If we have not found it, then again the while loop will run with the new left and right pointers. It will search in the remaining array until unless it finds the target or the left and right pointers interchange their position and we are sure that our target does not exist in the array. So if we find the target, we will return it from here. If we don't find it, then at the end of the day, we will simply return minus 1. So now let us calculate the time complexity of this algorithm. So here I have taken number of elements equals to 16 so that we will have easier time to understand how division is happening. So we have to figure out how many times does this loop runs. Okay, because that is the only thing that will basically determine the time complexity here. So every time this loop runs, what we are doing is we are basically figuring out the middle and dividing this array into two parts. One part will actually have the target or can have the target and other part will be ignored based on these conditions. And then the same will happen with the new remaining part also. So what we are doing is at each loop, we are basically dividing the array into half again and again and again. So basically what we can say is that we are basically dividing the number of elements that we are dealing with at each pass of the loop. So first we have 16 elements. After one loop, we will have 8 elements because we divided it by 2. Then we will have 4 elements. Then we will have 2. Then we will have 1. Simple as that, right? So basically what we are doing is at each step or at each loop, we are dividing the original number of elements by 2 and then just checking in the remaining elements, right? So we can say that if we figure out how many times we can divide 16 by 2, we will have the answer, right? We will know how many times the loop will run, right? So let's just say we have 2 raised to the power x is equals to 16 because at each interval or at each loop, we are basically dividing by 2. So if we have to multiply 2 into 2 by x times to get the 16, right? And this is a very famous problem. If we want to figure out the x, then we will use logarithmic arithmetic. So x is equals to log with base 2 16, simple as that, right? And 16 is just a constant right now, right? But we can actually have n number of elements in our array, so we can remove 16 and use n here. So log base 2 n, where n is the number of elements. So number of loops that we will have to deal with is log base 2 n, and this is going to be the time complexity also. Now in binary mathematics, everybody just knows that the base is always going to be 2. So we can usually ignore the base and simply write everything like log n. So the time complexity is equals to log n.